Thank you so much for the introduction, Agatha. So first, I would like to thank the organizers for arranging this great conference. I would also like to thank everybody here for coming and, like Igor said, not go to the beach. Okay, so the main character of today's talk will be log-concave inequality. So here is what I mean by that. And this log-concavity might be a bit different from what Jonathan will tell us next. So only for this talk. Let's say that we have a sequence A1, A2 up to AN. We will assume this number is always non-negative real number. We say this sequence is log-concave if for any case strictly between 1 and n, the square of the cave number is greater than the product of the neighbors, k plus 1 number and k minus 1. For example, this sequence here is a log-concave sequence. This is because if you take 9 here, 9 square is 81. 81 is greater than 4 times 15, which is 60. Okay? And one of the, at least earlier reasons why people start studying log-concavity historically is because log-concavity together with positivity, so that all of this sequence is positive, this will imply unimodality, that this thing will first increases up to 1 maximum, decreases and disappears, just like COVID. It has disappeared now. Okay. And one of the quintessential example of a log-concave inequality is the binomial coefficients. Here, n is fixed and k ranges from 0 up to n. This sequence is log-concave because, well, we can simply do direct computation. Just take this ratio, you do the computation, and at the end, you will get that this is equal to 1 plus 1 over k times 1 plus 1 over n minus k. Because k is between 0 and n, this number is greater than 1. That's why it's log-concave. Okay? The second example, it comes from permutations with exactly k inversion, where an inversion here is a pair I and j, such that I is less than j, but pi I is greater than pi j. Okay? And already for this example, as far as I know, there is no explicit formula on computing AK. So you cannot use direct computation to show this is log-concave. Instead, what people usually do is that they write this generating function and then realize that, oh, what a coincidence. This is from EC1 section 3, EC1 chapter 3, that this number is the Q analog of n factorial. Okay? And then what is important here is that each of these polynomial, the coefficients are all 1. In particular, it is a log-concave sequence. Its known property actually proved by, the earliest reference I can find is proved by Tom Liggett, who is also from UCLA, that the product of log-concave product of polynomials for which coefficient is log-concave, the resulting thing is again log-concave. And that is how we know the original sequence is log-concave. Okay? Everything good so far? The speed is good? Okay. Okay, the third and maybe the last example for now comes from graph theory, where given a graph G, let AK be the number of forest with exactly k edges, where a forest is defined to be a subset of edges of a graph that do not form cycles. Okay? So the log-concavity of this sequence was initially conjectured by Mason in 1972, where in fact he actually conjectured this for all matroids. I'll explain what is matroid later in the talk. Okay? And it turns out to be a difficult problem. It was finally solved by Junhe in 2015 by using this technology that is called the combinatorial Hodge theory, which takes some idea from the Hodge theory from algebraic geometry. Okay? And I checked yesterday in the Wikipedia, if you go and check, the Mason's conjecture and this Hodge theory was cited by the International Mathematical Union as among one of the reasons for them to award the Fields Medal to Junhe in 2022. Okay? Everything good so far? Good. Thank you. Okay, so now we have seen 3 examples of log-concave inequality. The first one, or at least maybe the first 2, are at the level of a homework exercise. The third one, it took 40 years and a very advanced theory to finally solve the problem. Okay? So intuitively, it is very clear, it's very obvious that the third inequality is much more complex than the first inequality. Okay? However, for now, let me place a devil advocate. Okay? Let me try to be contrarian. Hey, Swee Hong, maybe the third inequality is actually trivial. After all, everything in combinatorics is trivial, right? Okay? Maybe that's an easy proof of this inequality, just that none of these combinatorialists have tried hard enough to prove it yet. Well, I strongly disagree with that. I strongly disagree with my devil's advocate. But, we are all mathematicians here. So if I want to say that my devil's advocate is wrong, I had better give a rigorous proof, or at least give a rigorous reason. By showing that he is wrong, by showing that my devil's advocate is wrong, by giving a rigorous frameworks where we can differentiate one log-concave inequality from the other. Okay? And by the way, I forgot to say this, but you see that the word, when I say the word complex here, this word still does not have a rigorous meaning yet. And one of the goals for today's talk is to actually define that rigorously. Okay? But before I continue, are there any questions? Is the goal clear? Our motivation clear? Okay. Good. And okay. So rather than going through matroid directly, I will actually took a slight detour and discuss poset inequalities first. This is because the setup for poset will be much cleaner. Okay? And here is what I mean by poset. We already learned from it from Igor a little bit, but let me just quickly recap it. A poset for today will always be a finite set. It will be a finite set X together with partial order on the elements. For example, this picture is a 4-element poset, A, B, C, D. An arrow from A to B means that A is less than B. An arrow from B to D means that it's B less than D. So here we have A less than B, B less than D, A less than C, and C is less than D. In fact, we actually also have one other relation, which is A is less than D. But I don't draw them because it's already implied by the rest of the arrows, by transitivity. Okay? And the object that I want to study from linear extension, from the poset, is the linear extension, which is again what Igor have defined, but let me just quickly recap it again. You can think of linear extension as a completion of the given partial order. For example, for this poset, there are 2 linear extensions, either ABCD or ACBD. And I write Lx equal to k. This means that x will be the k smallest element in the linear extension. Okay. And now, log-concavity appears very naturally in the poset in the following way. First, we will always fix an element x of the poset. Let nk be the number of linear extension such that x is exactly the k smallest element in L. It was first conjectured by Chung, Fishburne, and Graham in 1980. It was proved exactly 1 year later by Stanley that this sequence n1, n2, n3 up to nn is a log-concave sequence. Okay? And the proof of Stanley is very beautiful. It's a very elegant proof. It's something that you should, if possible, always should be taught in any graduate combinatorics class. The proof was done by using this tool that's called Alexandrov-Fenchel inequality. Forgive me for my pronunciation. I always fail to pronounce his name. So it's proved by using Alexandrov-Fenchel inequality for mixed volumes. Here is what I mean by a mixed volume. Okay? And I will state the definition for n dimension in the next slide. But for now, let us focus on dimension 2 just to gain some intuition. Okay? Let K and L be any convex bodies. Let K plus L be the Minkowski sum. So this is the collection of points, which is the sum of every point in K and every point in L. Look at the volume of this polynomial K plus L. And in fact, look at it when you scale it by A and B, where A and B are any positive numbers. In this case, we will consider it as a variables. It's not too hard to show that this volume, is actually a polynomial. It's actually a quadratic polynomial in A and B's. And these numbers, the coefficient of these polynomials, is what we call the mixed volume. Okay? And in fact, this idea of using this as a polynomial, it actually extends to dimension n. For general dimension, it was proved by Minkowski in 1903 that for any convex body, so here we actually need it to be convex. For dimension 2, actually you don't need it to be convex. It can be any bodies that has that is compact. But for n dimension, given n many convex bodies, take their Minkowski sum, scaled by L lambda 1 up to lambda n. Again, this volume is a homogeneous polynomial in the variables of lambda 1 up to lambda n. And the mixed volume is now the coefficient of these polynomials. Okay? up till here, everything good so far? The speed is good? Okay, thank you. And now, log-concavity appears in the mixed volume in the following natural way. First, we need to fix the K1, K2 up to Kn minus 2. We fix the last n minus 2 convex bodies. Okay? And we only allow the first 2 convex bodies to vary. And let V star be this mixed volume. It then follows that V star AB square is greater than V star AA times V star BB. This is what we mean by this is what we think of a log-concavity for the mixed volumes. And as far as I know, so this nowadays, this theorem is attributed to both Alexandrov and Fernhell. But according to my limited amount of German, Fernhell actually didn't really prove the inequality. He actually gives some sketch, and some part of it got really sketchy. It was only 1 year later that Alexandrov actually gave 2 different proofs of this result. But nowadays, we remember it as an Alexandrov-Fernhell inequality. Okay? And now, what Stanley did is that he realized that, this mixed volume can actually have combinatorial interpretation. If you choose your polytopes carefully, for all of these polytopes to be slices of a special polytope that is called the order polytopes, then when you put it into this formula, this number V star AB, V star A, V star BB, they exactly become the number of linear extensions that we saw in the Stanley's inequality. And from there, the log-concavity of that sequence that that we saw before follows immediately. Okay? Very beautiful proof. Okay? In fact, before I continue, are there any questions about Alexandrov-Fernhell inequality? And maybe about the specification? Good. Okay. Now, Stanley, in fact, actually proved something stronger. He noticed that, if you look at these polytopes, if you just change this K1 to K minus 2, when you fix it, you just change it a little bit, you can actually prove a more general inequality. And this more general inequality is nowadays either known as the Stanley inequality, sometimes they are also known as the Stanley generalized inequality. Okay? What it says as follows. Suppose that you can additionally fix extra D element, Y1, Y2, Y3 up to YD, and you only count those linear extensions such that all of these fixed elements from Y1 up to YD has a fixed value from L1 up to LD. And you only allow the value of X to vary from K from 1 up to N. It then follows that even with this extra condition, this sequence N1, ND1, ND2 up to NDN is still a log-concave sequence. And this inequality, the more generalized version, in fact, it also follows from exactly the same argument that Stanley used to prove the Stanley special case inequality, the one when it's D equal to 0. What he did is simply that he changed the choices of the order polytope, and then this inequality follows from the same argument with literally 0 extra amount of effort. Okay? And this fact will be important later. That this generalized version, the fact that it's actually require little, almost little to no effort, will be important. So just a bit of spoiler. But up till here, is this inequality clear? Okay. Good so far? Okay. Now, let me in the same paper where Stanley proved the Stanley inequality, he asked for when exactly the equality occurs. He asked for the equality condition for Stanley's inequality. Okay? By the way, you see that I put Stanley inequality in the bracket here. This is because, as far as I know, Stanley never referred to Stanley inequality as a Stanley inequality. Like, in the private correspondence, once I think I saw that he referred to this inequality as Chern-Fishburne-Graham conjecture. I think it's most likely out of humility. Okay, he's a very humble person. Okay, and usually when people ask for equality condition, this is because it's viewed as a benchmark. It's viewed as a benchmark for showing that you have achieved maybe the next level of understanding of the inequality. For example, proving isoparameter inequality, proving that the inequality is true is not that hard, but proving that the circle is the only minimizer, is the only one that satisfies the equality condition is actually take another 40 years between the inequality and the equality condition. Okay? And here's a quote by Gardner that I really like, which says that if inequalities are silver currency, then the one with the precise equality conditions are gold. Okay, and I actually thank Igor for actually finding this quote. This is a very good job. Okay, any questions so far about the question? Okay. Well, and this question turns out to be a very difficult question. Between Stanley asking it and until it got solved is like 42 years, but it was finally solved by Senfeld and Van Hendel for the case d equal to 0. In that in the special case, in the simple Stanley inequality, they showed that the equality can occur if and only if these three numbers inside your inequality are actually all equal. Okay, so that if you look at the picture, they must form a flat. Okay. Yes, question?
So sorry, d equals 0 is the previous case without the li's.
Yes, exactly, without the d variables. Okay. Thanks for the question. But feel free to ask any question at any point. Okay. And so this condition is is proved by Senfeld Van Hendel, and also maybe but in a way you can argue that this is not really what Stanley is asking, because as you can see, this condition is numerical, but it doesn't really tell you the geometric structure of the poset when it achieves equality. It doesn't tell you anything about the combinatorial structure of the poset, which is arguably what really Stanley wants to see. Right? In fact, this is actually not my own word. This is actually communicated to me privately by Senfeld and Van Hendel. They think that is actually really what should matter when you do equality conditions. And in fact, in order to really answer Stanley's question, they provide an equivalent condition, and this one is combinatorial. The condition is a little bit more complicated than the previous one, but what is important is that this condition is combinatorial, and what's even more important is that this condition is very efficient. That if you read through this carefully, you realize that if I want to check this condition, it took at most n squared steps. In particular, it takes a polynomial time to check. Okay? Now, so this is the case for d equals 0. And then it's very natural to ask, Swee Hong, what happened to d greater than 1? Well, in the follow-up work next year by Ma and Senfeld, so this is the same Senfeld as the previous one. Ma is the student of Senfeld in MIT. They proved that for d greater than or equal to 1, the numerical condition that comes from the previous work with Senfeld and Van Hendel, they still hold. That this inequality can only be equals if and only if these three numbers are equal to each other. Okay? But unfortunately, they did not manage to extend the combinatorial equality condition. Okay? That the condition, as far at least in that paper, still cannot be extended to d greater than or equal to 1. Okay? And then it again becomes a very natural question, right? That can we do this for higher dimensions, or maybe for all dimensions? Okay? And of course, everybody will hope that the answer is yes. But unfortunately, such an equality condition, such a goal for this project will most likely fail in the following sense. When d is equal to 1, this project actually is successful. That together with Igor, we actually find a combinatorial equality condition that's actually checkable in polynomial amount of steps. Here, the polynomial here actually goes up by 1. So rather than n squared step, we actually need to take n cubed step. Okay? And once you know that, at first you will think that, then maybe for d equal to 2, then it will be n to the power of 4, n to the power of 5, n to the power of 6. Unfortunately, when d is equal to 2, there's actually a phase transition. Somehow, when you go up just by one variable, this problem becomes so hard that it actually is not part of the polynomial hierarchy anymore, unless the polynomial hierarchy collapses. Okay? I will define what is polynomial hierarchy in the next slide, but now let me just maybe communicate a quote from a colleague of mine from computer science department, who say that, if polynomial hierarchy collapses, then we will need to go and reprint every single computer science textbook in the world. So that in the first page, they will say that, by the way, polynomial hierarchy collapses. Okay? And then you start studying computer science. Okay? Any questions so far about this inequality? About the result, maybe, before we continue? Okay. Everybody good? Okay. Okay, if that's good, let me define polynomial hierarchy maybe in the following way. So polynomial hierarchy is part of this thing called the complexity problems. And today we will only care about two types of problem: the decision problem and the counting problem. Decision problem, these are problems where the answer is always either yes or no. You are not allowed to say maybe. Okay? On the yes or no. While counting problem is a problem where the answer will always be a non-negative number. Okay? So for example, let's say that I care about 3 colorings of a graph. Then the right question to ask for the decision problem will be to asking that if there exists a proper 3 coloring of this graph. While the right question to ask about the counting problem will be to ask to find the number of proper 3 colorings. Okay? In particular, if you can answer the counting problem, then you can also answer the decision problem. Okay? And our polynomial hierarchy will be a subclass of decision problems. It will be either question that's either yes or no. Again, you are not allowed to say maybe. Let me just get. Okay, and at the basement of the level of polynomial hierarchy is the complexity class P. P here stands for polynomial. This is the class of decision problems that is solvable by deterministic Turing machine. The word deterministic will be important later. And for now, we can just think of Turing machine as a classical computer. Or maybe you can just ask the stuff that you do with C++, with Fortran, with Sage. Okay? And these are the set of problems that should be solvable in polynomial time. For example, suppose that I give you a graph, and I already give you a sum 3 coloring of a graph. Then I ask you, hey Jonathan, can you please check if the coloring of this graph is proper? And then Jonathan, who is very smart, who is very good at doing all of this stuff, he said that, okay, what I will do is that I will check every edges of this graph, check the color of the endpoint, see if they are equal. Okay? And because there are at most n square over too many of the edges, this check will take at most n square many steps. In particular, it will be polynomial time. Okay? At the next level is the complexity class NP. Okay? So it's a very common misconception, especially whenever I talk to my parents. They always think that NP is non-polynomial. Okay? But it actually stands for non-deterministic polynomial. What it means is that this Turing machine or your computer, at every step, it can branch out to 2 different parallel worlds. It can branch out to 2 different steps. Okay? Each of these branches will do their own calculation. And at the end of the calculations, you wait until all of them are finished. Then the machine will be like a parent and go like, hey, Swee Hong, have you done your homework? Hey, Swee Hong sister, have you done your homework? He will ask every single person like, is the answer yes or no? And if at least one of them say yes, then the parent or the machine will say that yeah, the answer is yes. If all of them say no, then only then the robot will say okay, yeah, then the answer is no. Okay. For example, now maybe let me say that I'm asking Ashley, like, can you please check if this graph has a proper 3 coloring? Okay. It's widely believed that this problem cannot be solved in polynomial time. But instead now, if I allow Ashley to do non-deterministic Turing machine, what you can do is that each branch of the calculation correspond to an arbitrary 3 coloring of the graph. And then each branch will now check independently if the assigned 3 coloring is proper or not. We already know from the previous slide that this can be done in polynomial time, and therefore this problem can be solved in NP. Okay. Is the example clear? P and NP? Okay. Now we move on to the next level, the Turing machine with an oracle. In this next level, this Turing machine, they perform just like any other non-deterministic Turing machine, except that at every step, they have one extra option. That one extra option is that this Turing machine is allowed to call Terry Tao. Okay, yeah. This machine is allowed to use an oracle. It's guaranteed to be able to answer any specific combinatorial problem. And this oracle is so wise that it can answer everything in one step, and the answer is always guaranteed to be correct. Okay? but only one answer per turn. Okay? And of course, as far as if you call Terry, I think he's nicer than Oracle. He will actually explain some of the steps on how he derived that. But we assume that this Oracle can only say yes or no, will not tell you anything about any steps to use to solve the problem. Okay? And here's an example of a problem that is believed to be not in NP, but can be solved if you are given an oracle. So let the problem is that given a graph G, check if there's an induced subgraph of size exactly n over 2 that is not tree-colorable. Okay? And to help you, I will also provide an oracle that can check if a graph is tree-colorable or not. What you can do is that now each branch of the Turing machine will correspond to an induced subgraph of size n over 2. And then once you have your subgraph, you just call your oracle and ask like, hey, oracle, can you check if my subgraph is tree-colorable or not? Of course, we believe that nobody can do that, but because it's oracle, we assume that to be so wise that it can answer in one step. And that solves this problem. Okay? Up till here, is the Turing machine clear about all of this, the oracle? Is everything clear? Okay. Okay, now we are ready to define the complexity class. And at the bottom of the polynomial hierarchy is the complexity class P, P for polynomial. This is the level 0. Level 1 is the complexity class MP, the non-deterministic polynomial. For level I in general, these are the complexity class for problem that is solvable by non-deterministic machine assisted by an oracle that can solve any problem from level I minus 1. So it is and it is not hard to see that this actually forms a hierarchy. That sigma 0 is part of sigma 1, part of sigma 2, of the sigma 3. And the three example that we saw from before, the checking of tree coloring, checking for tree coloring, checking for probableness, checking for induced subgraph. These problems are from sigma 0, sigma 1, and sigma 2. It's widely believed that this containment is strict, that the second problem cannot be solved by P, the third problem cannot be solved by NP. However, nobody has been, as far as I know, nobody has an idea how to do that, and maybe most people actually maybe even already give up on trying to prove this. But in fact, it's widely believed that not only that, there's a question? Yeah? Okay, anyway, it is widely believed that this containment is strict, and in fact, something even stronger is conjecture. So it's widely believed that this hierarchy is strict, that this polynomial hierarchy does not collapse, in the sense that sigma 1 is not, so there's something in sigma 2 that's not in sigma 1, there's something in sigma 3 that's not in sigma 1, in sigma 2, and so on. Okay? So one special case, which is like, if you can prove that sigma 0 is equal to sigma 1, that is equivalent to prove that P is equal to MP. This is one of the 7 million problems. If you solve this, then you get $1 million. The collapse at level 1, which is saying that sigma 1 equal to sigma 2, this is slightly weaker. This is equivalent to say that MP is equal to co-MP. So this means that if you solve this problem, you might get $500,000, maybe not the full 1 million, but you might get $500,000 depending on how good you are at negotiating. Okay? Yeah. Anyway, sorry, let me get some water. Yeah. Any questions so far? Any questions so far about the polynomial hierarchy? Yeah. In any case, it's widely believed. It's widely believed that this hierarchy never collapses, just that nobody has an idea how to do that. Okay. And I must say that I have known some people who actually does not believe in Riemann hypothesis, but they all believe that P is equal to MP. P is not equal to MP. And these same people usually also believe that this hierarchy does not collapse in general. And so much actually now that I think nowadays is actually part of, usually is used as part of the assumption in many papers in computer science. Okay? Okay, now using this idea from complexity theory, we can now restate our main result. What our main result is saying is that consider the decision problem where given a polytope P, given a number D, given a number K, check if the Stanley inequality has equality or not. Then our result says that for D greater than equal to 0 or 1, this problem actually is in polynomial time. This is because we have combinatorial inequality condition that's not only combinatorial, it's actually so nice that this condition can be verified in polynomial time. However, for d greater than or equal to 2, somehow this problem becomes so hard that not only that it's not in MP, not only that it's not in co-MP, it's actually not in any of the polynomial hierarchy, unless the hierarchy collapses, and in that case, well, at least somebody will get $500,000. Okay? This is our first main result. Any questions so far about this result? Yes, questions, William?
Yeah, so by polynomial hierarchy collapses, you mean like you're not saying everything is in P?
That's a good question. Yeah, so by polynomial hierarchy collapses, it means that at some point, this sequence will stop at, let's say, sigma 3 or sigma 4 or sigma 5. In fact, I would say that the beauty of this work, okay, oh, sorry, maybe humble brag, is that we actually do not know where the polynomial hierarchy will collapse. We just know that if this is not true, it will collapse somewhere. Exactly where, unfortunately, or maybe fortunately, we don't know. Okay? Any other question? No? Happy? Okay. Now, let me just go back a little bit to the geometry part, which is the Alexander-Fenchel inequality. So remember that Stanley inequality is a special case of Alexander-Fenchel. So in particular, now that we know that the equality for Stanley is hard, then it follows almost immediately that the equality for the more general inequality, the Alexander-Fenchel, will also be very hard, in the sense that it's not in the polynomial hierarchy unless the hierarchy itself collapses. Okay? Now, notice, let me make a remark, which is that before our work, there's actually a very beautiful work of Seinfeld and Van Hendel, so the same people who proved the case d equal to 0, where they provide a complete geometric description of Alexander-Fenchel inequality. Okay? However, notice that their geometric description does not contradict our result. After all, I mean, if there's contradiction, then somebody must be false. But the reason there is no contradiction is because their condition, even though they are very, very beautiful, very like it's a complete description from geometric point of view, but from the complexity theory point of view, these conditions are monstrous. These conditions are so complexly intractable that it actually takes at least exponential time to actually solve them. Yes, question, Greta? There is a very good question. How do you input the polytopes? So that is actually something that we actually put as a red color here is what we call the unimodular polytop. The way we input it is that we describe the polytop as an intersection of hyperplanes. So we tell the computers the normal direction for each polytops and the equation that needs to satisfy. For each facet, yes. That's how it got inputted. The reason why we need to restrict to this class is because actually, what I just want to say is that already for this very specific class, there's unimodular polytop where all of these height functions are nice. This problem is already hard. It's actually harder. This problem actually is also hard for general polytops, but those are just a special case. That just falls immediately from this result. Okay. Any other question about the problem? Yes, question.
So if the polynomial time hierarchy collapses, do you know this question's in the top level?
So can you say louder? Sorry.
So like, you say if it's not in pH unless pH collapses. If pH collapses, do we know it's in the top level of pH?
That's a good question. Like, I guess what your question is that how do we prove this result? There are two ways to prove this result. The first one is to prove that every problem inside this is harder. And then there's like this. It's like comparing between a tiger and then maybe an elephant and then a mastodon and so on. And then we say that this problem is at the top, like the super giant. That is not how we prove it. What we prove is that saying that this complexity problem, they are like aliens. They do not even belong to any of these things. They are not even animals. They are like something that comes from Mars. So we do not actually. So that, I think that answers your question. Yeah, that we do not prove that this thing is pH hard, if that is what you're asking. But in a way, I think that's actually make this problem this theorem more beautiful because it allows us to actually do a method to prove something that do not actually use the standard argument in complexity theory. Just prove something is MP hard or maybe prove something is pH hard. Okay. Any other question? Oh, let me just mention here is that this Seinfeld Van Hendel, they have a geometric description, but that description actually is computationally intractable. In fact, it must be. Because if somehow somebody, or maybe I hope somebody can do that, if you can find some condition of this equality that's actually is efficient, then you will win $500,000 or maybe 1 million. Okay? Any other question for this result? Yes?
Proving that it's C equals P complete?
That's a good, yeah. So we do not prove it's C equal to P complete.
Okay.
Yes.
All right.
Yeah. Okay. Now that we have learned something from complexity theory, remember that our goal is to show that one log-concave inequality can be actually made rigorously harder than the other one. Let us see if our result can achieve that. And to do that, I will need to define the complexity class sharp P. What is this class about? This is the class of counting problem now. So so the answer is a number rather than a yes or no. And let me mention that again, this is a mistake that my parents make, that many people think that sharp P actually means that this is a problem that can be solved in polynomial time. But that's not the case. The problem that's solvable in polynomial time, the counting problem solvable in polynomial time, is actually called FP. Sharp P is believed to be, we don't know how to prove it, it's believed to be a strictly larger class where these are the problems where the numbers, the answers, can be expressed as the number of yes branches of some non-deterministic Turing machine. For example, let us talk about the number of proper tree colorings of a graph. The Turing machine, the branches will correspond to an arbitrary coloring, and the yes one will be the proper one. Will be the one where every edges have a different color. Okay? Another example is a number of linear extensions. The branches of the Turing machine, they all correspond to the arbitrary total ordering or arbitrary permutation of the poset, of the elements of the poset. Yes you reply yes if and only if this arbitrary total ordering actually is consistent with the given partial order. Okay? Now, without further delay, here is our main result. And we say that for d greater than or equal to 2, the defect of Stanley inequality, so the difference of these two numbers, is not in sharp P unless the polynomial hierarchy collapses. Okay? Okay, everything good? Yeah? So notice that both these numbers, ndk squared and ndk plus 1 and ndk by minus 1, we have already seen from the previous slide that this number is in sharp P. But and there are indeed some problem in combinatorics where the complexity is not in sharp P. But those problems, they are not in sharp P for trivial reasons. For example, some problems are not in sharp P because it's too big. Like you want to count something that's size of e to power of n. Okay? In which case, the sharp P is not the right class to work on. However, in our case, we already see that these two numbers are in sharp P, and so it's already not so big. The difference, which is supposed to be smaller, and you should expect it to be is less complicated to compute, actually becomes more complicated to compute. Okay? And I find that to be pretty unusual. In fact, it's so unusual that, to the best of my knowledge, the only other result in the literature where somebody proved in combinatorics something that is not in sharp P is the following work by Igor Pak and Panova in 2022, where they show that the square of characters is not in sharp. The square of character of Sn. Characters of Sn is not in sharp P. Okay. So in a way, you can, I believe, and somebody please correct me if I'm wrong, that this is, as far as I know, the first result in algebraic combinatorics. Yes, question?
When you say the square of characters, is that a difference of character? Or just...
Yeah, no, the square, the square of characters, yeah, not the difference.
The character of a irreducible representation evaluated at some class, and then you take the square. So
I see. Okay. Yeah, that makes sense. Thank you.
Yeah. Okay. Then let me just make again. Correct me if I'm wrong, Greta and Igor. That this result is, I think, the first result in algebraic combinatorics showing something not in sharp P. And in that sense, you can think of this one as the first result in, let's say, enumerative combinatorics or maybe order theory, showing that something is not in sharp P. Okay. In fact, maybe you know what? Don't believe me. Don't believe me that this result is unusual. But I will try to convince you instead by showing you some examples of other inequalities of combinatorics and see if they're in sharp P or not. For example, here is our binomial log-concave inequality that we saw at the beginning. This inequality actually has a combinatorial interpretation in the following way. Let KACBD be the number of pairs of northeast lattice path, so this path can only go up or go right, of these 4 points A, B, C, D in the plane or in the integer lattice, two-dimensional integer lattice. Then, if your A, B, C, D is these 4 specific points, it follows that n choose k square, which is the number that in the left side of inequality, can be expressed as the KACBD. The n choose k minus 1, n choose k plus 1, the right side, can be expressed as KADBC. So this gives an combinatorial interpretation to the inequality. In fact, not only that, this interpretation actually gives a combinatorial proof of the inequality. The way to see it is that because of the position ABCD that we choose, the path counting by the right-hand side will always intersect at some point. Then, take the first intersection, swap the color. Red becomes blue, blue becomes red. Then you will get a path that's counted by KACBD, and it follows that this mapping is actually an injection, that this actually gives you an actually injective proof of this inequality. In fact, not only that, because of this proof, you can see that the difference actually has a combinatorial interpretation. The difference is exactly the number of pair of this lattice path that do not intersect at all. It's a combinatorial interpretation. In particular, this is in sharp P. So this is one example, the first example of inequality that we have seen, and this is exactly in sharp P. Any questions so far about this inequality? Okay. The second inequality is the edge correlation of spanning trees that Igor has shown in the previous talk, where E and F are distinct edges. This TE is the number of spanning trees of this graph that contain the edges. This difference, in the paper of Feder and Mihail, they give an interpretation of this difference as a square of some numbers of electrical network. But there's actually an easier way to show this in sharp P. The way to do it is just look at this number. Remember that the number of spanning tree can be computed by matrix tree theorem. That is a determinant of some matrix. In particular, determinant can always be computed in polynomial time. It's a very efficient algorithm by using Gaussian elimination or by using QR decomposition. Because it's known that if something is FP, if something can be done in polynomial time, the difference is also in polynomial time. And that gives an easy proof or direct proof that this number is also in sharp P. Okay? And what our main result is saying is that our Stanley inequality, the Stanley inequality is different. It's different from binomial inequality and edge correlation inequality in a very rigorous manner. That this number is not in sharp P unless the polynomial hierarchy collapses. That's what makes Stanley inequality so special. Okay? And in particular, as a consequence of this result, it follows that this defect of Stanley inequality, that this inequality has no combinatorial interpretation. And of course, I will need to define what is combinatorial interpretation before I can make this statement. And for that, I strongly recommend everyone to go to read this paper by my co-author, by Igor Pak, of what is combinatorial interpretation. Pak, I think also 2022, where in this paper, it is explained very thoroughly why sharp P should be the right definition of combinatorial interpretation. Okay? Okay, you either read this survey, or you can ask Igor directly after the talk. One of them. Okay. If there are no, for now, let me just. I remember that I promised you to prove something about matroid, right, at the beginning of the talk. So let me try to do that in the last 5 minutes. And for that, I hope everyone can forgive me that I will skip the definition of matroid. But for this talk, you just need to remember 2 things. There are 2 special kinds of matroid. So you can think of matroid as information of 2 things. One is the ground set, which is always a finite set. And it will be another thing will be the collection of subset of ground set that's called independent set. The two special ones that you need to remember for this talk is first one is a graphical matroid, where the ground set is the edges of a graph, and where the independent set is the collection of edges that form a forest. The second one will be called a realizable matroids, where X will be any finite set of vectors over any field. In particular, we only care about dimension 2, F2. And our set I, our independent set, will be set of any linearly independent vectors. Okay? Now, the log-concavity for matroid, there are many, many results on this. But today, I will only focus on one of them for a good reason. I will, okay? Now, first, you need to fix disjoint subset of the ground set, or disjoint subset of your vector space. Call it S, S1, S2 of the SD, just like with the Stanley's inequality. You count the number of bases, or you can think of a number of spanning trees of the graph, such that the number of edges that come from set S1, S2 up to SD is fixed, just like with Stanley inequality, and only the one that comes from the special set S is allowed to vary. Okay? And it's believed, it's now proved that this sequence, BD1, BD2 up to BDN, is a log-concave sequence. It was first proved by Stanley in 1981 in the same paper where he proved the Stanley poset inequality for all regular matroids. And it was finally extended to all matroids by Alan Yen, who is in the audience, in 2023 as one of the problems in his thesis. And I think as far as I know, it has been up in the archive since 16 hours ago. Okay? So this is the result. And the reason why we care about this inequality, at least for this talk, is that notice that when you take your G to be a graphical matroid, this IK is exactly the number of independent set with K elements, is exactly the number of forests with exactly K edges, which is what we have seen at the beginning of the talk. Okay? And the reason why this IK is, the connection between this B and I is that there is a way, which I give here, but let me just skip them. There's a way to convert the log-concavity for this BK to get this log-concavity for IK. In particular, by proving this Stanleyian inequality, you actually find a new proof of Mason's inequality. That this Stanleyian inequality is strictly, or maybe at least as a stronger tool than Mason's inequality. Okay? Now, our result is that, similar with Stanley, that this defect of Stanley inequality is not in sharp P unless polynomial hierarchy collapses. This is the same as saying that just like with Stanley poset inequality, that turns out that two of the Stanley inequality, both of them are complicated. That they do not have that the difference do not have combinate interpretation. That you will hope that any injective proof is bound to fail. Again, unless the polynomial hierarchy collapses, and then you get your $1 million. Up till here, are there any questions about the main result? No? Okay, if there are no questions, then let me ask you a question instead. So, unfortunately, our works still have some small gap. The small gap is that, remember that all our result, it only applies either to d greater than or equal to 2 or d greater than or equal to 1. We still strongly believe that even when d equal to 0, which is the simplest case, the difference is still not in sharp P. The only reason why we cannot do that is the limitation of our tool. It's because we are trying, we do all of this by studying the equality condition. But for equality condition, we already know, right? When d is less than 1 or maybe d is less than 2, they are all in P or in co-MP. And that is not enough to prove not in sharp P. You need something that's higher than that. And yes, question, Zachary?
Yeah, for the Stanley inequality, I thought you said when d equals 1, you had some sort of claim about sharp P.
Not d equal to 1, but d equal to 2.
So for d equals 2, you said it's not sharp P.
Not sharp.
I thought you said there was something for d equals 1 that was...
This result, yes, let me go back to that. Sorry that it will take some time.
Thank you.
This one, yes. So what we say is that it's the equality condition, not the difference. Okay. Yes, but good question. Yeah. That's the reason why we cannot go through that. We cannot prove this in sharp P. Okay. Yes, question?
In the previous slide, there's an equality characterization.
Yes, that's a good question. There's an equality characterization for this one. But this number, all of them will take exponential time to compute. So they cannot be done in polynomial time. Yes. And in fact, it must be like that, unless, of course, okay, it's like this. If I can do that, today's talk will not be about Stanley inequality. Today's will talk about how I prove that polynomial hierarchy collapses. Okay, and I think that is all I want to talk about today. I thank you so much for listening.